Hi, so welcome to the second part of this week. So this is a video about exponential generating functions. So what is this about? Well, this is essentially just a definition. If you have a sequence, A0, A1, A2, and so forth, well, we can write it in the usual way as an exponential, as a generating function, or you can do it as an exponential generating function. What does that mean? Well, you write A0 plus A1x, so forth, so good. But now you have A2 divided by 2 factorial times x squared, and then A3 divided by 3 factorial times x to the 3 plus, and so forth. So in general, it's the sum from r equals 0 to infinity of AR divided by r factorial times x to the r. And of course, this looks very much like what you might have seen in calculus. Now, why is it important, or where does it turn up? Well, it turns up when order is really important when talking about functions. And we will see some examples which will make this more clear. Okay, so here's the problem. So you have the letters M, A, M, M, A. And the question is, how many words can you make of length 3 using these letters? And so this is a problem we could have encountered much earlier. And so here's the first way how we can do this. And so, well, how you do that? Well, you think about, okay, so A can be used at most 2 times. In that case, M has to be used just 1 time. Or A has to be used 1 time and M 2 times. Or A is not used at all and only M is used, namely 3 times. These are the only possibilities because we have 2 letters A and 3 letters M. And so here I wrote them all down, AAM, AMA, MAA, AMM, MAM, MMA, and MMM. So there are 7 possibilities. These are the 7 here. Now, if you just look at this case, we are now talking about 3 words of length 3, where we have 2 A's and 1 M. How many are there? This was something we talked about already before. These are the arrangements, and where the symbols are not all distinct. And we had that formula 3 factorial divided by 2 factorial times 1 factorial in this case, or 3 factorial divided by 1 factorial, 2 factorial, or 3 factorial divided by 0 factorial, 3 factorial. And if you think about what this is, well, this gives you 3, 3, and 1. Okay, but there's the second way how to do this, and this is the way which is much, much more useful when you have more complicated examples than just this, very small one. And for this, we'll try to use exponential generating functions. And so, okay, so let's try to do this. And okay, so let's look at first let's look at the letter A. Well, the letter A can occur 0 times, 1 time, and 2 times. And so we will write this as 1 divided by 0 factorial, so just 1 plus x plus, and now finally here something happens. So this is, you should think about this as 1 divided by 0 factorial. This is like 1 divided by 1 factorial times x, so just 1 times x. And this is, well, 1 divided by 2 factorial, so 1 half x squared. So what am I doing here? Well, so in this case, we have like 0, 1, and 2. And so we count this here as 1, 1, 1. But we do that with a little extra factor where you divide by the factorial. So 0 divided by 0 factorial, divided by 1 factorial, divided by 2 factorial. And why do we do that? Well, it will turn out this will precisely correspond to these factorials here. Okay, let's do it for the M part. Now in this case, again, well, it could happen that we don't use it at all. We use it once, twice, or 3 times. These are the only possibilities. In that case, we've seen it's not possible that we don't use it at all, but we don't know a priori, so let's just do it like this. So again, we have 1 divided by 0 factorial, which is like 1. 1 divided by 1 factorial, which is 1 times x, so it's x. And now we have 1 divided by 2 factorial, half squared. And in this case, we get 1 over 3 factorial, x to the 2, which is, of course, 1 over 6. And I really, let's try to write all the factorials. Okay, just to make the things clearer here. Okay, so this is exponential generating function in this case, just for looking at the possibilities for A, the one possibilities for M. And now we just multiply it, just, because this worked out pretty nice previously, so maybe it also works out here. So if you do that, we get, we get a big polynomial. And let's just call these coefficients A0 and A1, A2, and so forth. But we will always want already, so the result should also be an exponential generating function. This is important. So if you multiply exponential generating functions, you really want them also to be exponential generating functions. So, well, it's always, how do you do that? Well, we just have to keep track of these factorials. So this should be like this. And so forth. It goes up until x to the 5. And so, but for a moment, this is not, let's just write it like this. And so, now what is this A3? What is this? Well, let's just compute that, So what is A3? Well, A3 divided by 3 factorial x to the 3 is equal to, okay, let's check this out. We have to multiply this times this. So this is 1 divided by 0 factorial times 1 divided by 3 factorial times x to the 3. So let's just write the x to the 3 part here. Next one is this times this. So this is 1 over 1 factorial and 2 factorial. And this together gives us again x to the 3 plus, now we are here, 1 over 2 factorial times 1 over 1 factorial times x to the 3, so we get this answer. Okay, so I know this kind of looks complicated, but if you now figure out what is A3, what will we get? This has to be equal to that. We have to bring the 3 factorial on the other side, and what do we get? Well, it's 3 factorial divided by 0 factorial, 3 factorial. And voila, we get precisely the answer we already had before. See, this plus this plus this was 7. So get the same answer. So this is really a I really like this one. It's kind of, so this of course works quite in general. And if you think about why is it true, well, it's the same kind of argument as before with the generating function when we did this, when we said, okay, we could put the balls in the first part or in the second part. Precisely the same argument will show you that this is also true, but in this case we also carry around all these factorials, and these factorials, because they just fit nicely together, will precisely make up for the fact that now not all the symbols are distinct, and so therefore we have to divide all these factorials out. And so this is how you use generating functions. Now, what if you would know that if you would only count the number of words of length 3 where there has to be at least one A in there? How do you make up for that? Well, you just look here. This was like the exponential generating function for the letter A. And in this case, if you want that there is at least one A in there, you would just delete this term here, because you want to be at least 1 in there. You would start from x, not from x to the 0, but x to the 1. Okay, and you see now again how you can easily modify this, so that's very, very nice. Okay, so let's look at this example here. So we want to count the number of words of length 9 over this alphabet. So where additionally B should appear at least once, C should appear an even number of times, and D should then appear an odd number of times. So how do you do that? Now the trick is here to use exponential generating functions. And so the claim the answer is the following. The coefficient of x to the 9 divided by 9 factorial in the following. So what we do is we compute the exponential generating function, and then we know the answer will be the coefficient of this term here. And again, so we look at the case of A. So what about A? Well, A can appear arbitrary number of times. Not at all, or maybe just once. And so you get this infinite series here. Well, not really infinite, because, of course, it can appear almost 9 times in that case, because that's the case you're interested in. But I will say something more about this in a second. Because if you think about it, is it really necessary to restrict yourself to this? No, not at all. So you would get, because you're only interested in the coefficient of x to the 9 divided by 9 factorial, we can actually let this go to infinity. Because, well, any of the higher terms, which are larger than, like, so it's something in term of degree 17, well, that will never occur if you're looking at this term here. Well, for this computation, it just doesn't matter. If you have something really large or a really large term, if it is there or if it's not there, if you're only looking at that coefficient of that term of degree 9, in your computations, you will never use that. So you can really go on forever in this case. So this is very important. So always really convince yourself whether you can do this or not. In this case, you can do it, because there's no other restrictions on A. So what about B? B appears at least once. So we start from x divided by 1 factorial plus x to the 2 divided by 2 factorial, x to the 3 divided by 3 factorial. And again, in this case, you might think we only go on up to x to the 9 divided by 9 factorial. But of course, we could also add all the up, and we do that. We just add lots of higher terms, because for that computation it doesn't matter, but as we will see in a second, it will make things much easier. So it would be correct if you go only up to x to the 9 divided by 9 factorial, but for the computation it's actually much easier to go to the infinite. So to look at the infinite series instead of a polynomial. And why? Because, well, that's what we're going to see in a second. Let's just finish this. So C appears an even number of times, so that means it could appear not at all, absolutely. So we have 1 plus and finally D should appear an odd number of times. Like this. Okay, so why is this looks very complicated? But now, wait a second, now here comes the trick. This is something you've already seen, namely this is the exponential function. And what is this? That is nearly the exponential function, but there's only one, the constant term is missing, so this is e to the x minus constant term, minus 1. And what about this one here? Well, here we're missing out on the odd terms. So there's always a trick how you can do this. Whenever you have any such infinite series and you want to miss out on the odd terms, all you do is you take the series like this, e to the x, you add e to the minus x, and you divide by 2. So for instance, think about an odd term. If there's an odd term here, that odd term will also be there, but with a minus. Because minus 1 to the k, if it's odd, gives you minus 1, otherwise it's just plus 1. And so it will cancel out. But the even terms, they will survive. And the even terms, they will appear actually twice, and that's why you divide by 2. So check this out. This is the same thing. And now for the odd one, we just do this. Again, in this case, the odd ones will now actually survive twice, so we have to divide by 2, while the even ones will cancel out. And so now we collect all of this. So now we collect all of this together. It's right here, e to the 4x we get this answer here. So let's maybe put a separator in here. And so, well, now why does this help? Because now again, we can, so in order to figure out what's the coefficient here, we have to convert it back. So let's convert it back. And so this is now e to the 4x is just, so e to the x, instead of the x, you plug in 4 x, so we get the coefficient of, at the 9th, we get 4x to the 9, so this is 4 to the 9 times x to the 9 divided by 9 factorial, and all the other coefficients, plus, no, minus e to the 3x, so in this case, we get 3x to the 9, so 3 to the 9, x to the 9, divided by 9 factorial. Now, plus e to the minus x, so we get minus x to the 9, which is minus 1 to the 9, x to the 9, divided by 9 factorial, and so forth. Oh yeah, here too. And now we here, now everything minus 1 divided by 4. Wow. Okay, but you know, we're only really interested in that coefficient, x to the 9 divided by 9 factorial. So all the other ones are different, of different order. So if you collect it all together, what do we get? So the answer will be, and I think I write it, give me some color. Let's write it on here. So the answer, the coefficient of this is, okay, so here we have 4 to the 9 divided, so the 9 factorial x to the 9, we collect that together. We're only interested in what is in front of it, so this is a 4 to the 9. Here we get minus 3 to the 9. Here we have minus 1 to the 9, which is just minus 1. And what about here? That's just minus 1. It's like minus 1 times x to the 0. We're interested in the coefficients in front from 2x to the 9 divided by 9 factorial. So this doesn't apply at all to us. Now we divide everything by 4. So if you like, think about this as being, if you look at the terms, you will get 1 point this. And that's, of course, how you should do it. You just collect all the terms together, and then you look at the front, what you have there, and that is precisely this answer. And, well, if you look at this, I don't think you would have guessed it or come up with this maybe a different way, but I might be wrong, actually. So finally, so really stress again, that you should look at the examples in section 9.4 to really get a grip of this concept. And so see you next week.